Hello and welcome everyone to the final session of our summer school. So we are pleased to have with us me, Kotak and Phung, who will be leading an interactive session on Symphony. About the speakers, Meet Kotak is an SM student in the Computer Science and Engineering Department at MIT, advised by Professor Tess Smith and Professor Saman Amarsinge. Meet earned his BS in Engineering Physics from University of Illinois Urbana-Champaign in 2023. His research focuses on machine learning systems for AI for science applications. And Tung Fong is a master's in engineering student in computer science at MIT, also under Professor Tess Smith, and a graduate research intern at Harvard University. His research focuses on utilizing geometric deep learning to investigate complex material phenomena and guide the design of novel materials. Please take it away.
Hey guys. We're gonna try to give you an interactive version of what you guys just saw. I guess we are being really ambitious here. As you can see, you can probably spend an entire talk on one of these topics. I think our point here is just to show you what these things can do. So if you're not able to go through all of our notebooks, that's fine. Feel free to interrupt us. Okay, in terms of logistics, so that's the link that'll take you to our branch, our sub branch for this tutorial. Now everything here, so we have 4 notebooks here. I'll try to go through them in reverse order. So you'll see the pretty pictures first, and then we'll slowly go into the math. We'll start with the QM9 playground, which is where you'll see the actual predictions by Symphony on the QM9 dataset. And then we'll go into the message passing part, which is what these GNNs normally do. And then we'll kind of do a deep dive into spherical harmonics and how we use them in our work. And then finally, there are some intricacies some nice things about how just E3NN works and what are these equivariant operations that you've been hearing about. So that's the agenda. Now, the first 3 notebooks can be run in Colab, but for some reason, Plotly times out when you try to run the 4th one. So for the 4th notebook, unfortunately, you would have to clone this branch and set it up locally. That's why I'm also front loading this, because that when Phung is giving his part, I can help around in terms of if anyone is having issues running this. But hopefully this works. This might take a while because it's downloading a lot of stuff. So it should take 5 minutes to download. And then we're just setting up an environment and installing it. Okay, so I will directly go to the notebook. And I guess you guys can. So okay, I guess I'll give you guys 1 or 2 minutes to just start the downloading.
Can you show the link again?
Sorry. Oh, really sorry. Let me put it in the chat. Oh. And I guess can people just raise their hand as they're starting this thing so that I have a rough sense of where everyone is.
Could you show the link for me?
Oh. I'll stay on the slide as well.
Thank you.
Nice.
I'm on the page. I'm having some trouble following the instructions.
Sure. Yeah. So I guess we can. Okay.
Yeah. Sorry. Thank you so much.
Okay. But I guess just to show people what they can do. So you can go to your terminal. Sorry. Wait. Something showing. The screen seems to be stuck.
Might take a second.
Oh, okay, okay. Sorry for that. It's lagging, okay, yeah. Ah. Oh, I see.
Yeah.
Nice, it's a 2-minute lag. Good, so this is what I did 2 minutes ago. So yeah, just like. I think I went back. Yeah. Also, because we're like depending on partly like these things might take a while to like run, so it's fine if you can't like run everything. I mean, like the insights of this tutorial are like independent of whether you can like run them.
You could try that option.
Oh, start again. Hello.
Just the one.
Yes, okay. It's back, thank you.
I also link
Okay.
it.
Oh, link again, wow. I should have picked like some 1, 2, 3 or something. Oh. Okay, thank you.
Can I know like which Python version should we use?
Anything.
Oh,
Yeah.
because it's giving up me some warnings, errors, or something like
What
required.
version are you on?
3.7.
Oh. Okay. More than 3.9.
Okay.
Yeah, I think 3.6, 3.7. So like, so the biggest issue here is actually NumPy 2.0. Like they broke every single thing, like matplotlib and. Yeah. So. I was like, okay, I will start going through the notebook, I guess, while you guys try to like prove this.
Does anyone need help getting set up?
Yeah.
I'm happy to help debug.
Okay.
Great. Good stuff like.
Okay, yeah, sorry for that, but okay, I can keep on showing pretty pictures while the debugging.
Knowing him because like.
I was just.
Going along.
Yeah.
Oh, so just to like set up the context here. So in Tess's talk, you saw that how we load up all of our fragments and then we auto-regressively predict what the next molecule is, right? So this, all of this here is just like plumbing to just load up like the QM9 data set. We kind of trimmed it down to like a few fragments.
Excuse me, can you make it much bigger?
Oh, bigger.
This may be.
Hopefully there's. Oh boy. Still. Ah.
Yeah.
Okay. Sorry for that. So yeah, so all of this is just plumbing to load up some QM9 fragments. And if you visualize these, oh yeah, the lag is kind of. Okay, I'm gonna go very slowly so that. Okay, so if you look at the fragments, in this case, I just loaded up like just one molecule.
Yeah.
So this is the molecule, and then this X thing is the target atom. Sorry for that, I think probably is kind of. Yeah. So the circle is the molecule atom, and then the X is the target. So this is, and then as you keep on adding
Yeah, I
more and more fragments, it's gonna get bigger. Sorry for the lag.
so no, I think.
Also, I haven't started predicting anything. This is just me like showing you how I have like chunked up the data. And then finally, if you look at like one of the. Yeah, I think this is still like something midway. And then at the end, if you look at the last fragment, it will be your complete molecule. Okay. Makes sense. So this is the input data that we have. Now, let's get Symphony to do this. Okay, so we are going to try to predict this whole thing using Symphony. Again, we might not predict the exact same thing because Symphony was trained on like a really big data set. But yeah, let's try. Okay, so yeah, all of this is just again plumbing so that we can like actually run inference on this model. Also actually, I did not ask this, but who has worked with JAX before? Oh wow, okay, nice. Good. It is similar to Torch. It's just more functional. And as a compiler person, I think it's the future. My bias there. But yeah, so this should just set up like all of the plumbing that you need to like run the predictions. And particularly in this case, what we'll focus on is, so fixed predictions is like our like prediction list, like what we want in the, what we're comparing against. And then fragments are basically like the chunked up thing I was like showing you, right? Okay, so let's go to the 3D interface that Ameya and Song made. So, okay, so let me explain. So again, just to be clear, we are going back to that one fragment, one molecule thing that I showed you before. And the question here is that, what does the next atom look like? So here, what you can see is, so again, the circle is your molecule atom. The square is your predicted atom. And now the cool part is the position probabilities. So because we just have like one atom, like the probability distribution is going to be like a sphere because you can like put it anywhere. And then there's also different spherical harmonic channels that you can like look at. And then Phung is going to talk more about like all of this like spherical harmonic channel work that was done in this. But okay, and so yeah, you can, and on the table, you can see all of the atoms. So like hydrogen, carbon, nitrogen, oxygen, and looks like here Symphony is saying that we should have a carbon atom here. Okay, so this was one fragment. Makes sense. Any questions on the interface?
What exactly are we looking at here with the big yellow?
Yeah, so that's the probability distribution.
Okay.
Yeah, so I can like turn it off. So yeah, this is your molecule. This is the target atom, and then this is like your predicted atom. Makes sense? Thank you. Yeah. Okay, so this was one fragment. Now let's get more fragments in, right? Yep. Also, in case like Bartley just doesn't want anything, just rerun it. Somehow it works. Okay, so now it's getting interesting. So we have two atoms now, and then so this blue thing is sort of that probability distribution. So before it was like that big blobby sphere thing, but now we have two atoms. So it's saying that okay, your predicted atom should lie somewhere in this blue sphere. And if you look at that square, yes, indeed. And then yeah, you can just look around.
So for each like radial ring,
Yeah.
bin you have like a set of spherical harmonics.
Yeah.
And are we looking at like one of those bins here, or is this all of them?
I think here particularly, I think it's just one of them. I think it just like decides which bin to put into. Yeah, okay, cool, yeah, looks pretty, but yeah, here it decided it was a hydrogen atom, as you can see. Earlier it was carbon, now it's hydrogen. Okay, cool. Let's build more. Oh, cool. So.
So you didn't tell it was a hydrogen atom?
No, it predicted, yeah. So that's where that like atom embedding comes in. So we put like an MLP, and yeah, it's able to, so it predicts two things. It predicts what atom should like we should place, and then like at what location we should place it. So yeah, so this is just us moving forward in the prediction pipeline. So now here you can see those, yeah, I'm just like playing with the position probabilities here. So the position probabilities here were these two blobs, and it decided to predict this one, like the square. Let's see here. Okay. Oh, and then also you can obviously turn on the edges as well, in case you wanna. At the end, this is a graph, so you can also look at the edges.
You have like a cutoff?
Yeah, yeah.
Basically up.
Yeah, so we have like a cutoff, and then yeah, so we build this. Yeah. Again, I think this is like coming from the data set. Yeah. Okay, and then I guess let's go into like sort of the final stages. So now, as you can see, it's like -1. So we are sort of picking something from the end of those like fragments. So the fragments get built up as you go forward in the list. And now we're just picking something that's like really at the end. Okay. Yeah, and if it's blank again, just rerun it. Cool. So yeah, so here, okay, I guess I'll show this one first. So yeah, here you can see it has added a lot of items. And then if you look at the probability distribution, it's that like really tiny thing. And like it makes sense because now as you keep on like adding more and more atoms, like your like the positions where you would like want to put your next atom kind of goes down, right? So makes sense. Yeah, sorry, like
Colors here?
you mean these things? I think they're like different atoms.
Okay.
Kind of items. And if you remember Tess's talk, we can have like a stop condition. In this case, the stop condition was that final molecule thing. I am not a chemist, so if this thing has a name, feel free to shout it out. I think it's just like a randomly generated like molecule from the QM9 dataset. But yeah, so at the end, once it reaches like its stop condition, it's gonna stop predicting. And yeah, you have your molecule.
Can a stop condition just be like a number of atoms? It's going to be quite general. Quite specific.
I think in this case,
So I think you either predict a stop token, so you know you're done generating the molecule, or the other stop condition we have is it stops generating after like 35 iterations.
yeah, try to see if there's any.
So at which step does it do that? At the initial?
Yeah, it does it at the focus step.
Okay.
Yeah, sorry to chime in from above.
Nice. Try to find the slides for it. Like he has like a big like 3 or 4 slides, but I guess okay, so it's fine. But like what are the different conditions we can follow? But okay, so this was the first notebook. I think this is the most painful one. After this, Plotly should be more forgiving. But yeah, any questions? Okay, cool. So so before I hand it off to Tung, I'm just gonna do like a quick summary of like the message passing notebook. But yeah, also was anyone able to like run this notebook? Oh wow, nice, okay. Yeah, I know this one like does take a while and like yeah, hopefully we'll figure this out with like Kodak. Okay, cool. So let's go to the next one. So yeah, so this was just to again point people again in the direction, right direction. It's the yeah, so here's the link. Link takes you to this thing. And then from here, we are now going into the third notebook. Okay. And so here's some like nice GitHub magic. So once you open the notebook at the top, just change it to GitHub to Colab. And it will open up Colab. Yeah, it's magic. Cool. And okay, so this is.
Can you show
Yeah.
that magic again? Can you show that magic again?
Oh, wow, nice. Okay, so go up. And just put like, so there's GitHub, right? Just write to Colab.
Oh.
Yeah. Nice. Cool. Yeah,
That's amazing.
I was hoping to have this for notebook 4. Okay, cool. Also this won't let you like save it. So just create like, so if you don't know how to create like a new copy, so just create like a copy in your drive if you want to like actually save or like play around with this. But okay, I will skim through this one. Okay, so for context, so here we're gonna try to go through like the NequIP architecture that you guys saw. For context, so if you remember like the Google talk that was given, like the GNOME paper, they use like NequIP as like their main architecture. So yeah, it's a very simple and elegant equivariant architecture, and it has all of the pieces that are found in all of these networks. Okay, cool. So what's our input here? So the input here is, this is, I was able to zoom in nicely. Cool. So the input here is positions, and then we'll just randomly like send it like some atom species. Again, in this case, it's pretty random. We're not like here the focus is on the architecture, not really like the task. So yeah, we're just giving it like randomly some position vectors. So endpoints and 3 is because X, Y, Z. And then this is like your adjacency matrix. So yeah, you just create like all of the relative vectors. So at the end, you have endpoints by endpoints, where like every position would be like the relative vector. And then, so the cutoff thing that you were saying. So in this, so when we did this, we created like a fully connected thing. So all of the nodes were like talking to everyone. But then we were just like, let's just stick to like, I guess pairs where like the norm is less than 2.5. So this is the input. And then JAX ecosystem has like this neat thing called giraffe, which lets you just create like a graph tuple. So you will have like your senders, receivers, which is just like the indices of like the 2 pairs, and then positions, and then atom numbers. Like I said, we just randomly initialize them to 0 here. So nothing too fancy. And then I'll also plot this graph so that you can see what we're, oh, I guess it's gonna complain because I did not run this one. Yeah, and in this one, there's a nice pip install at the top, so no dependency issues. Yeah, should run. Oh, also, and I guess as these things are running, I just wanna skim through like the architecture that we have. So again, the atomic number here is just like an embedding, we just pass it to like an MLP. And then like the fancy technology, like the fancy equivariant technology that we have here is this message function, where so this summation, like this aggregate is like all of the messages of like, so let's say the central atom, it has like all of these neighbors. It's gonna aggregate the messages over all of these neighbors. And this message consists of 2 parts. There's a radial part and then there's an angular part. So the radial part here is this. You just take the relative distance here. So that's your radial part. And then for the angular part, this is where all of our like expressive powers like contain, like this is where the tensor products come in. So you take, so YL is like your spherical harmonics. So you use the spherical harmonics to like sort of featureize that geometry. And then you use a tensor product to sort of mix in the information from that neighbor's like feature. So now you have, so now you took some information from the environment, like from like the geometrical environment, and you also took some information from like the node feature. And then you combine them, and then we apply a linear layer. So that's the whole angular part. Okay, I am running short on some of the programs, so I'll do a quick skim, but yeah, so once you go through like the whole giraffe thing, as you can see, pretty molecule, that's good. I'll just do a run through. Yeah, this is just some like, for those of you who are like new to JAX and Flax ecosystem, we just do like a simple, like this is what an MLP looks like. The API is very similar to Torch. Yeah, I'm just like running through simple, yeah, it has like a nice way to like print out what all layers you have. So a simple MLP again, dense, and then a layer norm, and then also again like a dense or linear layer. This is the atom embedding. And then this is like the whole, so that sort of algorithm that you saw on paper, this thing codes up the whole thing. Again, I would urge you to come back to this and like walk through all of the functions here. I'm just getting to like the punchline here, which is, so if you train this network at the end, yeah, I'm just gonna show you like the final, like, so we just do like one pass through this network. And the thing I just want to show you that like you started with like node features that were like scalars. And at the end now, when we like plot this out, you'll see like some vector features, and like these vector features are like the things that help you capture like more complicated higher order information. There you go. So each node here has like these vectors. So 4 vectors here. It's kind of arbitrary. You can play around with this, but they can represent like forces or like dipole moments, and yeah, different things. But okay, so that's it for my, oh yeah.
I'm sorry, I'm really lost. So chemically, what am I looking at?
So chemically, you are looking at a molecule here. Like I said, here the focus is not on the on the thing I'm predicting. It's a very toy example. You should go to the QM9 part if you want to see something real.
So those are all atoms and you're defining the relationship,
Yeah,
like
yeah.
if those are all carbon atoms.
Yeah.
What are the black lines?
These things?
Yeah.
Yeah, you can think of them like bonds. So they're edges here.
Well, I mean, chemically speaking, it wouldn't like.
Yeah. Chemically, don't try to look too much into it.
So, sorry, that's why I'm confused, but
No,
maybe it's just me. Everybody else seems to be totally.
I understand. Yeah. I think it's just like I think the input graph here is kind of a toy example. So
You just randomly generated a
yeah,
bunch.
just created a graph and we're like, can we learn like
Right, I'm just, if those were all carbon atoms, it just, if I was like, how would these arrange themselves in space? It wouldn't be like that, and that's why I'm.
No,
confused.
yeah.
These
So
points
why
are
is
just
it like
randomly
that?
generated. Like there's no chemistry informing like the positions of these points in this particular example.
Okay. That's the part I was confused about, thank you. Sorry.
Yeah, again, I'll repeat as a disclaimer, there's no chemistry happening here.
Yeah.
Okay, yeah, it's the 4th notebook where the chemistry is. Okay, cool. Okay, I'll hand it off to him.
Right, hi everyone. So Mint has told us about Symphony, this model that generates molecules one atom at a time, and also this 3rd notebook, which has gone through very briefly. These like equivariant message passing networks that form the foundation for parts of Symphony. And what I would like to tell you about next is more generally, to begin with, like the Python library that we use for this, E3 and N, where E3 is your Euclidean group in 3 dimensions. So this is a group that captures like the symmetries of translation, rotations, and inversion in 3D space. And E3N is the Python library for that Symphony is written in. And so I'd like to walk you through that first. So going back to the tutorial repo, this will be the first notebook, Introduction to E3N. And you can do the same magic as before, where you open up the tutorial notebook and then in the URL after GitHub, you can type in to Colab. All right, so in particular, this will be an introduction to E3N and JAX. There's two versions of E3N. There's one written in PyTorch, which is what you saw in Tessa's slides earlier, snippets of E3N Torch code. And this notebook will be in JAX. They're very similar. JAX happens to be a little bit faster and maybe becoming more popular for machine learning. So as before, you can run the first few cells and that will set your environment and everything you need to run this notebook. All right, so I guess just to get us started to motivate, like, why do we need E3N and what is it useful for? Informative to start with, just generally 3D rotations. A lot of physical systems that people are interested in modeling, it's important to capture this idea that if you rotate, or with your physical system, there's no inherent global coordinate system. And so if you rotate your system, the physics of it should transform in a predictable way. And so we'll get started by talking about rotation matrices. So a rotation in 3D can be described by 3x3 orthogonal matrices. And so the group of 3x3 matrices, where they're determined as one, is called SO3. This is the special orthogonal group. So this captures all rotations in 3D space. So any given rotation, you can capture in one of these rotation matrices. And then a related group is O3, the orthogonal group, and this includes both rotations and inversion in 3D space. And what I mean by inversion is inversion about the origin, where you flip all of the signs of your Cartesian coordinates. And so in this example, we define a few vectors, and then you can, in JAX, you can create a random rotation, or using E3N, you can create a random rotation matrix. And here, we're looking at the vectors, and then also the vectors rotated and plotting them. Turn the cell. Here we have your original vectors, and then the arbitrary rotation matrix that we've generated, and you can see the vectors here rotated. All right, so next moving on to more general transformations and sort of higher order representations of this, irreducible representations, which I'll get more into detail about that in a bit. So E3N gives us a way to build neural networks that you encode in these geometric constraints like rotations and translations. And so what do I mean by this? We can look at a few different examples to motivate this. For example, if you're working with molecules and you want to predict their energies, then energies are scalars. And so they don't transform under rotation, and they also don't transform under inversion. So this cell is, you're creating what's known as an Eric's array. And so that captures the data that you have. In this case, the type is of the Eric's array, it's 0e. So the 0 is referring to the order of the tensor. In this case, you just have a number, a scalar, and so it's order 0. If you have order 1, that's a vector, and then order 2 is a matrix, and so on for higher order tensors. And then the e is capturing that you have, that this is invariant under reflection. So if you reflect your physical system, then in this case, the energy should not change. And here's just an example of defining the Eric's array to represent your energy and then doing transformations of it. And then we'll see that under rotation and under reflection, you still have the same energy. Arbitrarily, we've chosen 0.5 here. Another type of quantity you have that you might want to model in physical systems is captured by pseudoscalars. And so these are scalars that change under inversion. One example of this is if you have a helix, then the handedness of the helix will change under inversion. So if you invert all the coordinates, then you'll go from either from a left-handed helix to a right-handed helix or vice versa. So this is important for when you want to model chirality, especially in the context of like organic chemistry when you have antinomers, where chirality changes the chemistry of your molecules. Okay, moving on to higher order representations of data types that you might be interested in modeling. So say you have a molecule or crystal and you want to predict forces on all the atoms. And so forces should necessarily change under rotation. If you rotate your system, the predicted forces on your atoms should rotate in the same way. And so you can represent these forces in Europe's arrays before, but this time you have the type of it is 1O. So 1 is referring to this is a vector instead of a scalar, and then O is that it changes under inversion. If you invert your system, then your force vector should also change. So you're defining an arbitrary force and then rotating and reflecting it, and you can see that each built into E3 and N, like the forces transform in a predictable way. So finally, the last example I did are pseudo vectors. So these are vectors that transform as you might expect a vector to under rotation, but under inversion they don't. They are also not inverted. And so an example of this is the cross product, where if you take the cross product of two vectors, it's also equal to if you invert the two vectors or negate them, you get the same value for the cross product. And so here, this next cell, we're defining two vectors, computing the cross product, and then also computing the cross product of like the negated vectors. And you see that you end up with the same cross product vector in the end. So this is showing an example of a pseudo vector. And so far we've looked at scalars, pseudoscalars, vectors, and pseudo vectors, all of which model like relevant physical quantities that you're interested in modeling physical systems. And so there may also be higher order features beyond scalars and vectors that you're interested in modeling. And so this is where irreducible representations come in. So representation theory, strange math that's related to group theory, tells you that there's actually infinitely many of these quantities like scalars, vectors, and higher order tensors. And representation theory tells you how these transform under like rotations. And so this is given by the Wigner D matrix. So for scalars, rotation doesn't affect them. And then for vectors, you have your normal rotation matrix. And then the Wigner D matrix tells you how higher order tensors will transform under these like rotation operations. And here's just diving a little bit more into the math into it. If you're curious, you can read this, but I'll skip over it for now. All right, and then here's just another example of defining an Earth's array where you're mixing two different data types. You have a scalar and a vector, and E3N in your data, it keeps track of sort of, you can pass in this whole array and it'll keep track that the first entry should be associated with like how scalars transform, and then these next three entries are how vectors transform. And then, okay, so we have these, you have your data represented in these different data types, these different irreps. And so in order to build up these equivariant neural networks that capture like the geometry of physical systems, instead of just doing like multiplication or some other operation, how we act on these irreps arrays in order to create new ones and then to build up the equivariant neural network is you do what are known as tensor products, in particular Clebsch-Gordon tensor products. And so what you can, this is showing an example of defining two different vectors, and then you compute their tensor product in E3 and N. So if we run the cell, it will give you the output of the tensor product of these two, and also the irreps that make it up. And so what you can see is there's a way to physically interpret these irreps. So for your first one, you get out a scalar from it, and this is actually proportional to the dot product of these two vectors. And that's because dot product is invariant under rotation. If you rotate your two vectors, then you will have the same dot product. And then the next irrep in this output of the tensor product, you have a vector, and this is a pseudo vector. And so similar to what we showed before, this is proportional to the cross product, two vectors. And then the final component that you get out of this tensor product is a higher order equivariant feature. And this corresponds to the symmetric traceless part of the tensor product of the two vectors. So if you're interested in learning more about this, just generally about tensor products and how you deal with these irreducible representations that represent your data, we have a recent paper all about the math behind the tensor product. Looks like I'm doing fine. So now we'll move on to the second notebook where we'll talk all about spherical harmonics, which are these functions that Tess talked about in the tutorial or in her talk earlier. And these build up sort of how we model the probability distributions in Symphony when we want to sample like angularly like where we should place the next atom. So if we go back to the GitHub, it's the second notebook now on spherical harmonics. And just like before, we can do the same magic for GitHub and then to Colab, and then you can open that up in Colab. Okay, so before I move on to the next notebook, does anyone have questions about this first one? Yes, Peter.
So you have to use these operations that are built into the library whenever you handle these verbs, right?
That's right.
So it's not like overloaded with the JAX.
Yeah.
JAX operations.
These are built on top of checks. Oh, yes.
So you mentioned like when you generate these, when you use an equivariant network, you typically set some maximum L, and then when you multiply, you do a tensor product between, you get ones that are higher than the originals, right? So you just truncate at that point, or what?
I think that's what's usually done, yeah.
I think it's like a design choice. So yeah, depending on whether we're gonna keep that, because it goes to 2L max, right? Like, it goes from
Exactly.
like 0 to 2L
Yeah.
max. So yeah, it's purely like a design choice.
I see. And then is it sort of scale badly if you just have, if you go up to 2L and every time every
Yeah.
layer you do, you wouldn't want to keep going 2L, right?
I mean, but yeah, I mean, obviously it's gonna like scale, like, yeah, it's gonna go up like bunnies, but yeah. But yeah, I guess depends on like where you wanna cut it off.
So
yeah,
that's a user choice. You set
Yeah,
at every
that's-
layer, you have some maximum.
exactly, yeah. We have just like a function, like, it's like a parameter, yeah. You just like tell it, chop it off, yeah.
Yeah, when you do the tensor product, you can also specify like which irreps you want to get out of it and keep only those irreps, for example. And so that's one way of enforcing this choice of like going up to a certain order of irrep or Lmax that you want in your network. Any other questions? All right, I will move on to the second notebook then. All about spherical harmonics. Right, so these are wonderful functions that form a basis for functions on a sphere. So in the same way, you have like polynomials that form a basis for like Taylor series, and also sinusoids that form a basis for your Fourier series. Spherical harmonics are the equivalent of that, but for functions defined on the surface of like on a 2D sphere. And so to be a bit more precise about that, I guess I should first run these two cells, set the notebook, be important for later. Right, so going back to the spherical harmonics. So what I mean by a function on sphere is you can specify like polar angle and azimuthal angle, and that gives you a position on the sphere. Here we're just dealing with the unit sphere. And the spherical harmonics are functions that they're indexed by two numbers, L, which is sort of like you can think of it as like the angular momentum or angular frequency of these functions, in the same way that in Fourier series, your different sinusoids have different frequencies. And then M is different spherical harmonics that have the same frequency that you need in order to span the whole space of functions. And so what's really nice is, as Tess mentioned in her talk earlier, we can visualize these spherical harmonics, and that's what this next cell is doing. So this is plotting, or this will plot the spherical harmonics for first three orders of L. So L equals 0. Okay, this is still generating. Right, so L equals 0, just like a constant on sphere. And then L equals 1, you have these lobes. And then also L equals 2. And so some of you may recognize that these are the same shapes as electron orbitals in your S and P orbitals. And that would be correct, because spherical harmonics are the angular part of these atomic orbitals. So new connection was forming mechanics there. As I mentioned before, as you increase L, that's increasing the angular frequency of these spherical harmonics. So they vary more rapidly over the sphere. And because of that, you can capture or you can express any signal in the sphere with high enough order of L. And there's an interesting connection here between spherical harmonics and that they transform as the irreducible representations or irreps of O3, so the group of 3D rotations. And so because of that, spherical harmonics are well suited to modeling like whenever you have like you need to deal with rotations of physical systems. Here, this is showing like how equivariant, how you can specify like points that you want to evaluate the spherical harmonics, and then how you go about doing that in equivariant. And another very nice property that spherical harmonics have is orthonormality. So they form an orthonormal basis, and so you can associate with any function on a sphere a unique decomposition into spherical harmonics. So like the coefficients that you have associated with your spherical harmonics that sum up, there's always a unique like one-to-one mapping between your tensor on the sphere and then what the coefficients associated with spherical harmonics are. And so this is diving a bit more into the nitty-gritty technical details behind that, and also showing short proof of using all these properties that from like your representation theory and spherical harmonics, how like they are indeed equivariant under rotations. Okay, so now we'll look at an example of how to use this to represent functions on the sphere. So our example in this case, it's a toy example where we want to model like a hexagon in the sphere, or just in general point cloud of 6 points. And so for this next cell, that will next 2 cells. So here we specified like the points of the hexagon, and then what this is doing is it's using equivariant to expand the points. So you can treat all of the points as like delta functions or like very peaked like signals on a sphere, and then you can decompose that into spherical harmonics. This is something that was also shown earlier in Tess's talk, where the higher order of spherical harmonics you up to, the more accurately you'll be able to express your signal. And so this is our visualization of the spherical harmonics, or no, of the signal of these 6 points. So the axes are a bit off, but it's really a hexagon. And then we can also create the signal using equivariant just from the Cartesian coordinates as well. And so now we'll look at how like, okay, so you have this signal and you want to expand it into spherical harmonics. We'll look at how that reconstruction of the signal changes as you use higher order spherical harmonics. And so the thing with spherical harmonics is that the order you need, like if you have some angular distribution on a sphere, then where the smallest angle between any 2 points you have, say, is you need like an L max or order of spherical harmonic that's at least like greater than or equal to 2 pi divided by that angle you have in order to resolve it. So say if you have a square, then you need at least like order L max equals 4, or a hexagon in this case, we'll see that we need at least spherical harmonics of order 6 in order to resolve that's like a pi over 3 angle between the points in the hexagon. So you'll see like for the first like expansions using lower L, then you don't get like an accurate reconstruction of the geometry. But then as you go to higher L, once you get to L equals 6, then you can faithfully capture this hexagon signal that you have. All right. And so this is sort of a bottleneck because a lot of times you may have signals where your angular resolution between points is quite small. And so in theory, you would need a very high order of spherical harmonics in order to capture your signal or your geometry. And so this is sort of an angular resolution bottleneck in a lot of in like modeling these systems, but there's one way to get around that, and we'll discuss that in a little bit. But for now, we'll look at how can you transform the signal that you have now that you have it. So we define a rotation matrix in equivariant, and then up here we can apply the rotation matrix and rotate the signal. So under the hood, this is transforming the spherical harmonics in a certain way using these like Wigner D matrices, and then turns out this rotates the signal as you would expect. All right, so now we'll move on to how you can represent probability distributions on the sphere. So this is especially pertinent for Symphony, where once you've chosen your focus atom and you to determine where you want to place the next atom, as well as the atomic species of the next atom, then the next step in the process is you want to determine the probability distribution over space or over the sphere of your focus atom of where you want to place the next atom. And so in order to represent this probability distribution, we need to understand how we can go from spherical harmonics inward into probability distribution. So like any probability distribution, we need to satisfy normalization. So the integral of the probability distribution over space equals 1, and it needs to be non-negative as well. And so the way of doing this, especially in machine learning, is you use the softmax function where you exponentiate your signal, and then you divide by like the integral of like all the exponentiated signals over space, and that gives you this ensures that you normalize it, and so it's a valid probability distribution. And there's functionality built into equivariant in order to do this, where you can apply the exponentiation operator and also integrate it in order to get a valid probability distribution. And so now the problem of learning this probability distribution becomes learning the spherical harmonic coefficients to represent your probability distribution, and then you can do the softmax process in order to turn it into a probability distribution from the spherical harmonics. Okay, and then going back to something I mentioned earlier, this angular frequency bottleneck, when you have like a geometry of signal that's the angular resolution pretty small and you need higher orders of spherical harmonics in order to capture it. So one way to get around this is to use different channels or multiple channels. And so one example might be, say you have a square, and so the angular resolution of that is like you have pi over 2, and so you would need spherical harmonics up to order 4 in order to capture that normally. But say if you use 2 channels with L max equals 2, then you can sort of have one set of spherical harmonics learn like 2 like opposite points, and then the other 2 points of the square. And so by using multiple channels, you can actually express these signals that would typically need higher order spherical harmonics, but using lower order, in this case just L max equals 2 with 2 channels instead of a single channel of L max equals 4. So this is how we can get around this angular frequency bottleneck when you're trying to represent certain signals. So now we'll talk about how you can actually learn these equivariant angular distributions. So the general goal here is you want to learn spherical harmonic, like say that there's a probability distribution that you want to learn. And so this task becomes like choosing the coefficients associated with your spherical harmonics such that it minimizes the KL divergence between the ground truth probability distribution and the one that you've learned from choosing like a certain spherical harmonic coefficients. For those of you who might not be familiar, KL divergence is a measure of like you can think of it as like similarity between 2 different distributions. And so really you want to minimize that to ensure that the distribution you're learning is as close as possible to the ground truth that you're trying to match. And so these next few selected codes sort of step you through that. And then here we're using in JAX this way of like sort of learning the coefficients and like using gradient descent to learn the coefficients that you need to represent this hexagon signal that we had before. In this case, we're only going to L max equals 2 and using 6 channels. So this allows us to capture the hexagon like geometry without using L max equals to 6. And so the reason you tend to not be able to go up to high L max is because this like tensor product operation that you want to often use in constructing equivariant neural networks is it scales polynomially with like the order of spherical harmonic you go up to. So it's a rather expensive operation. And so using multiple channels instead tends to be more computationally efficient while still being expressive enough. Okay, so this is finished during the training loop. Ideally, find the coefficients that we need to represent this distribution. So if we run this next cell, you can see it will plot the signal that we learned. And indeed, that we've been able to capture the spherical harmonic signal of this like hexagons toy example that we've come up with. And so this wraps up this notebook. Here we've shown like how spherical harmonics form a basis for functions on a sphere, and they're well suited to handling cases in physical systems where you care about like preserving like symmetries, and like if you like transform your physical system in a predictable way, like rotate it, then the things you want to predict, like forces or a probability distribution of like where to place the next atom, in this case of Symphony, that those are preserved. And this concludes our tutorial. Thank you. Any questions about this last notebook?
I guess like this way that you found of like getting around the limit for L, is this kind of is there like a more general approach to say like I can apply certain combinations of nonlinearities and aggregate them and then get something that's still equivariant? Like is this like a very special construction, or is it
Like using multiple channels?
or you using multiple channels and doing the softmax basically? Or is it I could kind of chosen something really different as long as it's maybe like a pointwise thing.
Yeah, I think as long as it's pointwise, it's fine. Like softmax preserves equivariance.
And then similarly with the multiple channels idea, that also.
As can jump in.
Yeah.
Yeah, I can just confirm. Yeah, so you can use any, as long as it's pointwise. So in this case, you're basically applying the activation function in real space on a scalar signal. And so that's still equivariant. And you can use any activation function. So we use the softmax in this particular case because we wanted to get something that's more peaked, something that's a probability distribution. But in general, it could be anything. As far as like, can you kind of generalize this idea to other operations? The trick here is that if you then wanted to go ahead and go back to reciprocal space, if you will, or Fourier space, or the IREPs, this signal would require higher bandwidth to accurately represent, but that doesn't mean you have to keep around all those higher L's. So I think there's a lot of interesting games you can play between doing activation functions in one space versus the other and projecting back and forth. I think that's actually quite an expressive operation. And in fact, like in E3NN, I know it's in Torch, I don't know if it's in JAX, we have like these S2 activations that are basically, you use these projections and activations as the primary activation function versus like a gate or a norm nonlinearity. So yeah, there's a lot of, it's just one example of many kind of games you can play.
Right, so I guess it kind of feels like in normal convolutions, you apply the filter and then you just apply some nonlinearity pointwise in real space. So I guess
yeah, but you can actually, yeah, you can definitely do it on the sphere, and that's actually in Equiformer V2. I think a lot of the activation functions are replaced with S2 activation functions.
So there's one other question, maybe?
Yeah, so spherical harmonics form a basis for like anything in 3D. Have you checked with like density functional theory or something if any of these activations are actually related to the electron structure? I mean, otherwise it's sort of a coincidence that they're related, right? It's just a coincidence of SO3.
I think SO3 is the reason, right, that they're related.
That's the coincidence I'm talking about. But do you actually get anything that's actually related to the real electron structures?
I don't think we've used GFT or like any sort of charge density prediction in order to like see if there's a relationship between like these spherical harmonics and the actual charge density. So it would be something that's interesting to look at though.
Yeah, I can add a little bit more to that. So yeah, it is just a mathematical thing. Obviously, you can use the spherical harmonics to, for example, express a local atomic basis. But in general, they're more expressive. They're going to be able to express things that are not related to quantum mechanics. So it is more of a mathematical construction. The reason why you have the orbitals in like quantum mechanics comes from the math, not the other way around. As far as like, you know, if you do force models, for example, I remember this was something that we were looking at a while ago. If you go through an intermediate like charge density and then predict forces, like that's not very well constrained. So I think in general, you'd have to put a lot of constraints over a spatial signal in order for it to really be interpreted as like a charge density. There are many other spatial functions that can be very expressive that you can use to make some other type of prediction. So I don't think it's, even if we were doing some intermediate state like that, I don't think it would directly correspond because it's like extremely under constrained. If that hopefully answers your question.
Yeah, thanks.
Any other questions? Thank you.